Problem one, interestingly, both Mars and Mercury have exactly the same accelerations of gravity. So they're telling you the accelerations for both planets. That's going to be A of t is negative 12.1 feet per second. A stone is dropped from a cliff and hits the bottom 4 seconds later. How far did it fall and what was its velocity on impact? Well, remember, we're going to have S of t, which is the position function. We're going to have V of t, which is the velocity. And we're going to have A of t, which is the acceleration. And when you go from the position function to the velocity to the acceleration, when you go to the right, you have to differentiate the prior function. So for example, if I have S of t and I want to try to find V of t, I would just take the derivative of S of t because that's what the velocity is equal to. So the velocity is equal to S prime of t. If I have the velocity and I want to find the acceleration, what I would do is I would take the derivative of the velocity to get the acceleration function. So when you move to the right, from the position function to the velocity to the acceleration, you differentiate. When you move to the left, you integrate. And that's primarily what you're going to be doing for these motion problems. They're going to be giving you the acceleration, which is going to be a constant. Here they're telling you on these two planets, I'm not sure how interestingly it is, here they're telling you that the acceleration is negative 12.1. What we're going to have to do is we're going to have to get the velocity function by integrating the acceleration, and then we have to get the position function by integrating the velocity. So what I suggest you do is write out S, V, A, and to the right you differentiate, to the left you integrate. So here I'm given A of t is negative 12.1. The velocity, V of t, is going to be the integral of the acceleration. So here the integral of negative 12.1 dt, or negative 12.1 t plus a constant. So the velocity is equal to negative 12.1 t plus a constant. Well, what else is told to us in this problem? It says a stone is dropped from a cliff. So at time 0, the velocity, V of 0, is 0 because the stone is not moving. It's starting off in your hand and then being dropped. Same difference with the position. When you take the S of 0, the position function is also 0. And this is what happens when you have a stationary object that's dropped. So since I know the initial velocity, V of 0 is 0, what I'm going to do is I'm going to plug in t is 0 and solve for the constant, right? Because it's negative 12.1 t, so it's negative 12.1 times 0 plus c. Negative 12 times 0 is 0, which means c is equal to 0. So what does that tell you? That tells you that your velocity function, v of t, is equal to negative 12.1 t. Now we want to find its position function, s of t. And what we're going to do is we're going to integrate the velocity. Because we're going from the velocity to the position function, we're going to the left, so we're integrating. So the position function, s of t, equals the integral of the velocity, which is negative 12.1 t dt. So the integral of negative 12.1 t is negative 12.1 t squared over 2 plus some constant. So here our position function is going to be equal to negative 6.05 t squared plus some constant. But since the initial position, what we're going to do is we're going to start off on this cliff. So we have these planets, so we have this cliff. So our initial position is going to be up top here. And I'm going to say that S of 0, the position at time 0, is going to be 0. So I'm going to evaluate S of 0. So that's going to give me negative 6.05 times 0 squared plus c. And I know that that's going to be equal to 0. So what that does is it tells me that in the position function, c is also equal to 0. And this is going to happen from time to time for these questions where your constants are both going to be 0. So here we know our acceleration a of t is negative 12.1. Our velocity v of t is negative 12.1 t. And our position function s of t is negative 6.05 t squared. And that's the challenge with these questions, is you being able to start off with the acceleration and then integrate to get the velocity and then integrate to get the position. So now we're going to go about answering these questions. The question first says, how far did this stone fall? Well, in order to answer that, the question said that it hits the bottom 4 seconds later. So the question is, how far did it fall? We're just going to take the position function and evaluate S of 4. So here we're going to go negative 6.05 times 4 squared, or negative 6.05 times 16. So here it's going to be negative 96.8. Now that's confusing because the question says, how far did it fall? Since we started off the question by saying at 0 seconds, the height was 0, this point up top is 0, which means it dropped 4 seconds and hit the ground 96.8 feet under where it started. So we're not going to say how far did it fall. It fell negative feet. That doesn't make any sense. So here we're just going to make that positive. So how far did this stone fall? It fell 96.8 feet. The question then said, what was its velocity on impact? While our velocity function is negative 12.1 t, it hit the ground 4 seconds later, so we're just going to evaluate v of 4. So that's going to be negative 12.1 times 4, or negative 48.1 feet per second. And the velocity can be defined as negative because the stone is moving downward. So for these questions, you start off with the acceleration, and the challenge is going to be to end up with the velocity and then the position functions from that. For problem 2, now we're going to take a trip to Jupiter, and it says the acceleration of gravity, a of t, is equal to negative 75.9. Now, it says we're basically repeating this first problem. So we know that we're on this cliff. It's dropped, and 4 seconds later it hits the ground. We're going to define the initial position of 0 to be at top of the cliff. The initial velocity, since the rock is being held in our hand, so we're going to say the initial velocity is 0 as well. So we're going to find the velocity function first by taking the integral of the acceleration. So here our velocity is the integral of negative 75.9 dt, which is going to be negative 75.9 t plus some constant. But just like before, since the initial velocity is defined as 0, here we're going to have, for v of 0, negative 75.9 times 0 plus c, and that equals 0, which means our constant is going to be 0. So our acceleration is negative 75.9. Our velocity is going to be negative 75.9 t. And then now to get the position function, we're going to integrate the velocity. So the key is just to remember to go from the position to the velocity to the acceleration. To the right, you differentiate. To the left, you integrate. So here our position function is the integral of our velocity, negative 75.9 t dt, or negative 75.9 t squared over 2 plus c. Negative 75.9 divided by 2 is negative 37.95 t squared plus some constant. But since we assume that s of 0 at the top of the cliff was also going to be 0, I plug in 0 for t, and that's going to give me negative 37.95 times 0 squared plus c, and s of 0 is defined to be 0. So that makes our constant c equal to 0. So our position function, s of t, is negative 37.95 t squared. So that's the third of the three functions we need to find. The acceleration, which is given to you. The acceleration is always a constant. It's always a number, the acceleration. So the acceleration is a constant. We have the velocity and we have the position. So now the question says, what is the distance that this stone has fallen? Well, we're under the same conditions as problem 1. So it said after 4 seconds and hits the ground. So here we're going to find s of 4. So that's going to be negative 37.95 times 4 squared, or negative 607.2 feet. And once again, the reason why it's negative is because we started off assuming that s of 0 is 0, so the height at the top of the cliff was 0. It dropped 607.2 feet. So we say our answer for the distance is 607.2 feet. Then what was the velocity on impact? So that's going to be evaluating v of 4. So here our velocity function, negative 75.9 times 4, or negative 303.6 feet per second. And since it's falling downward, the velocity, they tell me in the science world, can be negative. So there's our answers for that one. Problem 3, a particle moves horizontally along the x-axis according to this formula, and x of t is the position at time t. Okay, so this is a little bit different. Here, they're not giving us the acceleration. Here, they're giving you the position function. So I'm going to change it so it looks like the previous two. I'm going to change this into s of t equals, and then you see the rest. Here they want us to find the velocity and the acceleration. So remember how this works. We have s, v, a. When we move to the right, we differentiate. When we move to the left, we integrate. But now they're giving you the position function. So to get the velocity, I'm moving to the right. And since I'm moving to the right, I differentiate. I go back to the first trimester. The velocity, v of t, is equal to s prime of t. So that's going to be equal to 3t squared minus 12t plus 9. And that's it. That's the velocity. To find the acceleration, we're going to take the derivative of the velocity, or the second derivative of the position. So I'm just going to go back to my velocity function now and find the derivative again. So I'm going to have 2 times 3 is 6t minus 12. So those are our functions. The velocity is 3t squared minus 12t plus 9. And our acceleration is 6t minus 12. Find the two intervals of time when the particle is moving, and I believe this last word should be moving up. So we're starting off with this position function, x of t, which we changed as s of t. And what I did was I plugged that equation into my calculator. And I went to the table of the calculator and started off at 0 because you have a position function. So you always have to start off with the time being defined as 0. And I looked at the table of values that I have. So if you look at your table of values, you see that at time 0, the function is -2. At time 1, the function is +2. After 2 seconds, the function is 0 again. So we're going from -2 up to 2, and then back down to 0, and then -2, and then back up to 2 again. So it looks like, according to the table, from 0 to 1, it starts off at 0, -2. If I kind of do a better job at drawing a graph here, here's my axis. When x is 0, y is -2. When x is 1, y is 2. When x is 2, y is 0. So it's going up from 0 to 1. So the first interval that it's moving up is from 0 to 1. Then it kind of goes back down to 0. And then when x is 3, y is -2. But then after 4, it goes to 2, 5, it goes to 18, 6, it goes to 52. And if you scroll down on your table, it's going to be increasing forever. So I'm going to say from 0 to 1, that first interval, it's increasing. And then from 3 to positive infinity is the second interval that the x values create y values that increase. Finally, find the velocity when the acceleration is 0. Well, when is the acceleration going to be 0? When is a of t going to be equal to 0? Well, I have the acceleration function. I have it as 6t minus 12. If I set that equal to 0 and solve, I get t is equal to 2. So that means a of t occurs when a of 2 equals 0. So that means 2 seconds into this particular path, the acceleration is 0. Well, the question said now find the velocity when the acceleration is 0. Well, now I'll go back to my velocity function. V of t is 3t squared minus 12t plus 9. But I know the acceleration is 0 when t is 2. So this is just a fancy way of asking you to do v of 2. And when you plug in 2 to the velocity function, here the velocity, v of 2, is going to be equal to -3. So the velocity of the function when the acceleration is 0 is -3. The last problem in this video is problem 4. And it says a car is going 80 feet per second, which is approximately 55 miles per hour, and it hits the brakes and it comes to a full stop in 5 seconds, assuming there was constant deceleration. We'll talk about that in a second. Find the formulas for the velocity and the position function for the car at time of 0. And then we got to try to figure out what was the total distance the car traveled until it came to a complete stop. Well, what do we know in this particular problem? It says the car is going 80 feet per second. So what that is the velocity. So we're going to say that the velocity at time 0 will start off when this car is about to hit the brakes. So just before the car hits the brakes, that's going to be time 0. So time is 0 when you hit the brakes. And we're going to say that the velocity at that time was 80 feet per second. Now, one definition that you want to know about is the acceleration is equal to the change in velocity over the change in time. The acceleration, a of t, equals the change in velocity, delta v, over the change in time. So in this particular problem, it says that the car is going 80 and then it's stopping. So it's basically going from 80 down to 0. So we're going to say that the velocity goes from 80 to 0. Well, when it's going 80, the time is 0. So these two match up. So at time 0, the car is going 80. And then it says the car stops in 5 seconds. So at 5 seconds, the velocity is 0. So here our acceleration is going to be equal to 80 minus 0 over 80 divided by 0 minus 5, or negative 5. So here the acceleration, a of t, is going to be equal to negative 16 feet per second squared. So this is a formula that you want to know. The acceleration is equal to the change in velocity over the change in time. But that's what we needed right now. We needed to have this acceleration function, because now once we have it, we're going to work backwards, because the question is asking you for the velocity and the position function. So remember our chart, the position, the velocity, the acceleration. When you go to the right, you differentiate. When you go to the left, you integrate. So here we're going to be integrating. Here I have the acceleration. So the velocity, v of t, is equal to the integral of the acceleration, a of t dt. So the integral of negative 16 dt, or negative 16t plus a constant. So here our velocity, v of t, is equal to negative 16t plus c. But this one here, the constant is not going to be 0, because we know this. We were told that this car was going 80 feet per second, or 55 miles an hour. So I know that v of 0, so it's negative 16 times 0 plus c, I know that v of 0 is equal to 80. So here I'm going to solve this for the constant. So negative 16 times 0 is 0, which means the constant c is going to be equal to 80. So that means our velocity is equal to negative 16t plus 80. So that's what our velocity function is going to be. So the acceleration, the change in velocity over the change in time, was negative 16 feet per second squared. Now our velocity is negative 16t plus 80. We're going to now integrate again to get the position. The position function, s of t, is equal to the integral of the velocity, dt. So the integral of negative 16t plus 80, so s of t equals negative 16t squared over 2 plus 80t plus some constant. So here our position, S of t, is equal to negative 8t squared plus 80t plus c. Well, in order to start these questions, you have to pick a starting point. So you have this car that's driving 55 miles per hour, and then at some point, it decides to hit the brakes. So this is the starting point when the car hits the brakes. That's S of 0. And we say that the position is going to be 0. So that's one rule that we're going to use. Then it says it's going to brake and stop after 5 seconds. So that means our position at 0 is going to be defined as 0. So I'm going to use that to figure out what the constant is for this position function. I'm going to plug in 0 for all the t's, and that's going to give me a 0 value, which means in this position function, the constant is going to be 0. So here our position function, S of t, is going to be equal to negative 8t squared plus 80t plus 0. So here is, besides a reminder, here is our position function. So the question said find the formulas for the velocity, which we did, and for the position, and what was the total distance traveled until the car stopped. Well, the question said that the car stops in 5 seconds. So that's just a fancy way of saying what is the position. Remember, we're starting off in this chart here. We're hitting the brakes at time 0. It's stopping after 5 seconds. I need to know what this distance is. I need to know what the position is. So we're going to evaluate the position function at 5. So it's negative 8 times 5 squared plus 80 times 5, or that's going to give us 200 feet. So this car, traveling 55 miles per hour, needed 200 feet to stop.